The universe is vast beyond comprehension, containing billions of galaxies, each harboring countless stars and planets. For centuries, humanity has gazed up at the night sky and wondered the same fundamental question that has captivated our species since we first developed consciousness. Are we alone? Is Earth the only planet in this infinite cosmos that harbors life? Or are there other worlds out there teeming with alien organisms we have yet to discover? This question has driven our greatest scientific endeavors, inspired countless works of fiction, and shaped our understanding of our place in the universe. For decades, scientists have been searching for that one definitive piece of evidence that would finally answer this age-old mystery. They have built increasingly sophisticated telescopes, developed cutting-edge detection methods, and analysed data from thousands of distant worlds, all in the hopes of finding that smoking gun that would prove we are not alone. And now it appears that moment may have finally arrived. Recently, a team of researchers from the University of Cambridge made what could potentially be the most groundbreaking discovery in human history. Using the most advanced space telescope ever constructed by our species, the James Webb Space Telescope, these scientists detected something extraordinary in the atmosphere of a distant planet called K2-18b. What they found was a molecule known as dimethyl sulfide, or DMS for short, floating around in this alien world's atmosphere. Now, you might be thinking, so what? It's just a molecule, right? Well, here's where things get incredibly interesting. On Earth, DMS is produced in only one way that we know of, and that's by living organisms. Specifically, it's created by marine phytoplankton and other biological processes. In other words, every single instance of DMS that we have ever encountered on our planet has been the direct result of life itself. The implications of this discovery are absolutely staggering. If this detection is confirmed and accurate, we may have just found our first concrete evidence of alien life. Not microscopic bacteria preserved in ancient rocks, not mysterious radio signals from space, but actual, active biological processes happening on another world right now, producing molecules that we can detect from over 100 light years away. But before we start celebrating first contact with extraterrestrial life, we need to take a step back and examine this discovery with the critical eye that such an extraordinary claim demands. As the legendary astronomer Carl Sagan once famously said, extraordinary claims require extraordinary evidence, and the claim that we have found alien life is about as extraordinary as it gets. The planet in question, K2-18b, is located in the constellation Leo, approximately 124 light-years from Earth. Now that might sound incredibly far away, and on a human scale, it absolutely is. The distance is so vast that it's almost impossible for our minds to truly comprehend. If you could travel at the speed of light itself, it would take you 124 years to reach this distant world. But here's what makes this discovery even more remarkable. On the scale of our galaxy, let alone the entire universe, K2-18b is practically right next door to us. Think about that for a moment. If life in the universe is as rare as some scientists believe it to be, finding two inhabited planets so close together would be like randomly dropping 2 grains of sand anywhere on Earth and discovering they landed just millimeters apart in the middle of the Sahara Desert. The odds would be astronomically small. This means that if K2-18b truly harbors life, it wouldn't just represent humanity's first contact with alien organisms. It would also be incredibly strong evidence that the universe is absolutely teeming with life. It would suggest that Earth is not some unique cosmic accident, but rather just one among millions, perhaps billions, of inhabited worlds scattered throughout the cosmos. The stakes could not be higher. This discovery has the potential to completely revolutionize our understanding of biology, chemistry, astronomy, and our place in the universe. It could fundamentally change how we view ourselves as a species and reshape our entire worldview about life beyond Earth. But as excited as we might be about this possibility, we must approach these claims with healthy skepticism and rigorous scientific analysis. The history of astrobiology is littered with false alarms and premature announcements that later turned out to be incorrect. From the supposed discovery of microbial life in Martian meteorites to mysterious radio signals that seemed artificial but turned out to be natural phenomena, scientists have learned to be extremely cautious when making claims about extraterrestrial life. So what exactly did these researchers find, and how confident can we be in their results? To understand this, we need to dive deep into the cutting-edge science behind this potentially paradigm-shifting discovery. K2-18b was first discovered back in 2015 by the now-retired Kepler Space Telescope, which spent years hunting for exoplanets by detecting the tiny dips in starlight that occur when a planet passes in front of its host star. At first glance, K2-18b didn't seem like the most promising candidate for harboring life. The planet is dramatically different from Earth in almost every conceivable way. For starters, it's much larger than our home planet, with about 8.5 times the mass and 2.6 times the radius of Earth. It orbits much closer to its parent star than we do to our Sun, completing a full orbit in just 33 Earth days. And speaking of its parent star, that's very different from our Sun as well. Known simply as K2-18, it's what astronomers call a red dwarf star, about half the size of our Sun and producing only about 2.5% of the Sun's total energy output. In the search for extraterrestrial life, scientists typically focus their attention on planets that are similar to Earth, operating under the assumption that Earth-like conditions are most likely to support Earth-like life. And it's fair to say that K2-18b is anything but Earth-like. However, despite these differences, the planet does orbit within what astronomers call the habitable zone, that sweet spot around a star where liquid water could potentially exist on a planet's surface. The breakthrough came in 2019 when scientists made a discovery that changed everything. They detected water vapor in K2-18b's atmosphere. Now, water vapor alone isn't considered a definitive biosignature because we found it in all sorts of places throughout the solar system that almost certainly don't harbour life. But this discovery was still monumentally significant because it marked the first time that water vapor had ever been detected in the atmosphere of an exoplanet orbiting within the habitable zone of its star. This 2019 study relied on data from the aging Hubble Space Telescope, and while the detection was relatively faint and limited in resolution, it was compelling enough to convince NASA that K2-18b might be worth investigating further with their newest and most powerful instrument, the James Webb Space Telescope. In 2023, they did exactly that, and the results were absolutely fascinating. While the James Webb data didn't definitively confirm the original water vapor detection from Hubble, it did provide strong evidence for the presence of other molecules in K2-18b's atmosphere, including methane and carbon dioxide. But most intriguingly of all, the telescope detected just the faintest trace of that potentially game-changing molecule, dimethyl sulfide. Initially, nobody was particularly excited about this finding. The detection was weak, with what scientists call a statistical confidence of only 2 sigma. In practical terms, this meant there was about a 5% chance that the signal was just random noise rather than a real detection of the molecule. In the world of scientific discovery, this level of uncertainty is generally considered insufficient to make any definitive claims. However, a follow-up study published earlier this year raised that confidence level significantly, bringing it up to 3 sigma. This improvement meant that there was now only a 0.3% chance that the signal was a statistical fluke, rather than a genuine detection of DMS in the planet's atmosphere. The study, published in the prestigious astrophysical journal Letters, was extremely cautious about mentioning the possibility of alien life. Astronomers have learned to be very careful with their language when it comes to potential biosignatures, largely because every previous claim of this nature has eventually been disproven. But the project's lead researcher has been far more optimistic in his public statements. In press briefings following the publication, he described the DMS detection as absolutely astounding and potentially revolutionary. In his words, these findings represent the first hints we are seeing of an alien world that might actually be inhabited by living organisms. Naturally, this kind of bold statement sent the international media into an absolute frenzy, with headlines around the world proclaiming that scientists had potentially discovered alien life. But the critical question we must ask ourselves is whether this excitement and media attention is actually justified by the scientific evidence. On the surface, the logic seems remarkably solid and compelling. The study found very strong evidence for the presence of DMS in K2-18b's atmosphere, and DMS itself appears to be extremely strong evidence of biological activity. But as we're about to discover, the situation is far more complex and nuanced than it initially appears. To truly understand what these scientists accomplished and whether their conclusions are warranted, we need to examine the incredibly sophisticated and challenging process they used to detect molecules in the atmosphere of a planet located over 700 trillion miles away from Earth. The method these scientists used to peer into the atmosphere of such a distant world is nothing short of extraordinary, and understanding this process is crucial to evaluating whether their claims hold up under scrutiny. When K2-18b passes directly between its host star and our telescopes here on Earth, we witness what astronomers call a transit. During this cosmic alignment, the planet blocks a tiny fraction of the star's light, causing a barely perceptible dip in the star's brightness, as observed from our vantage point. This technique, known as transit photometry, is how the Kepler telescope originally discovered K2-18b in the first place, but with telescopes as advanced as James Webb, scientists can push this method much further. Here's where things get truly ingenious. While most of the starlight hitting the planet is simply blocked during a transit, a minuscule sliver of that light actually passes right through the planet's atmosphere before continuing its journey to Earth. And by analysing this atmosphere-filtered starlight using a technique called transit spectroscopy, researchers can learn an incredible amount about the molecules that light encountered during its passage. Think of it like this. Imagine you're looking at a distant streetlight through a coloured piece of glass. Different coloured glasses will absorb different wavelengths of light, changing what you see on the other side. Similarly, different molecules in a planet's atmosphere will absorb light at specific wavelengths, creating a unique fingerprint that scientists can read and interpret. The end result is something that looks like a cosmic barcode, a spectrum showing which wavelengths of light were absorbed and which made it through unimpeded. By reading the gaps in this barcode, the missing light, so to speak, scientists can identify which molecules were likely responsible for those specific absorptions. But here's where this seemingly straightforward process becomes extraordinarily complicated. Transit spectroscopy is incredibly difficult to execute properly. For one thing, we're only interested in an absolutely tiny fraction of the star's total light output, just the bit that travelled directly through the exoplanet's atmosphere. This means that before scientists can even begin their analysis, they must somehow tease out this minuscule signal from what is essentially overwhelming background noise. Even if they manage to extract the signal successfully, interpreting the resulting spectrum is nowhere near as simple as scanning a barcode at the grocery store. Atmospheric conditions can alter the signal in countless ways, muting certain features, masking others, or shifting various aspects of the spectrum in unpredictable directions. To accurately read and interpret these spectral fingerprints, scientists must understand numerous parameters about the exoplanet's atmosphere. They need to know things like how much cloud cover or atmospheric haze is present, what the temperature gradients look like at different altitudes, and how atmospheric pressure changes throughout the planet's atmospheric layers. Here's the fundamental problem. For K2-18b, we simply don't know these crucial atmospheric parameters with any degree of certainty. The planet is so far away and so different from anything in our solar system that we're essentially making educated guesses about its basic atmospheric properties. Scientists have developed an ingenious workaround for this challenge using advanced computer modeling. They create thousands of potential atmospheric scenarios based on their best estimates of conditions on the planet. For each of these simulated atmospheres, sophisticated models generate synthetic spectra and compare them to the real spectrum captured by the telescope, searching for the closest possible match. It's an elegant solution to an incredibly complex problem, but it comes with significant limitations. Planetary atmospheres are phenomenally complicated systems with countless variables that influence how they interact with light. We could never simulate every possible combination of atmospheric conditions, so scientists are forced to make assumptions about which scenarios are most likely and focus their analysis accordingly. This is precisely where the K2-18b study begins to encounter serious problems. The research team that made headlines around the world focused their entire analysis on one key assumption, that K2-18b is what scientists call a Haitian world, essentially an ocean planet with a hydrogen-rich atmosphere. They used atmospheric parameters consistent with this type of world and specifically tested for gases that would be expected in such an environment. This approach isn't necessarily wrong. The Haitian world hypothesis does fit reasonably well with the limited data we have about K2-18b, but it's absolutely not the only scenario that could explain the planet's characteristics. Some scientists believe K2-18b is more likely to be a magma world, covered in an ocean of molten rock rather than liquid water. Others suspect it might be a mini Neptune with no solid surface at all, just layers of increasingly dense atmospheric gases. The fact that three such dramatically different planetary scenarios remain viable possibilities reveals just how little we actually know about this distant world. More importantly for our discussion, each of these wildly different atmospheric environments would produce completely different spectral signatures for any given set of molecules. That impressive sounding 3 sigma confidence level for the DMS detection is only valid if the research team's initial assumptions about K2-18b being a Haitian world are correct. And many scientists in the field believe those assumptions are fundamentally flawed. Just a couple of weeks after the publication of the bombshell paper claiming evidence for alien life, a physicist from Oxford University decided to reanalyze the exact same spectral data using a different atmospheric model with different underlying assumptions. His conclusion was startling. There was no evidence for DMS whatsoever in K2-18b's atmosphere. The fact that two different teams of highly qualified scientists can examine identical data and reach completely opposite conclusions should give us serious pause. It's a clear indicator of just how challenging and uncertain transit spectroscopy really is, especially when we're operating at the very limits of our current technological capabilities. This is science being conducted at the absolute edge of what our instruments and theoretical understanding can handle. We're pushing the boundaries of detection, trying to identify incredibly faint signals in data that's already barely above the noise threshold. Under these conditions, the results become highly sensitive to the assumptions and methods used in the analysis. But let's step back for a moment and consider a hypothetical scenario. Let's assume, for the sake of argument, that there really is DMS floating around in K2-18b's atmosphere, and that the Cambridge team's detection is completely accurate. Even under these generous assumptions, we still face another significant problem that could undermine the entire alien life hypothesis. DMS has long been considered an excellent biosignature candidate, precisely because it's exclusively produced by living organisms here on Earth. Every single instance of DMS that scientists have studied on our planet has been the direct result of biological processes, primarily marine phytoplankton and other microscopic life forms. However, our understanding of this molecule has evolved considerably in recent years, and what we've learned is somewhat troubling for those hoping to use DMS as definitive proof of alien life. Scientists have begun discovering DMS in places throughout our solar system where we know with absolute certainty that living organisms could not have produced it. In 2024, researchers detected DMS in the tail of a comet within our own solar system. This discovery was particularly significant because comets are essentially barren chunks of ice, rock, and dust. They have no atmosphere to speak of, no liquid water, and certainly no biology capable of producing complex organic molecules. Yet somehow, through currently unknown non-biological processes, this lifeless celestial object was harboring what we previously considered to be an exclusively biological signature. This finding forces us to confront an uncomfortable reality. Just because a molecule is only produced by life here on Earth doesn't necessarily mean it can't be created through non-biological processes elsewhere in the universe. The cosmos is vast and strange, filled with extreme conditions and chemical processes that we don't fully understand, particularly on exoplanets that are radically different from our home world. If we know that DMS can be produced without life, even if we don't yet understand the specific mechanisms involved, how can we be certain that any DMS detected on K2-18b was necessarily created by living organisms? The honest answer is that we simply cannot make that determination based on this evidence alone. This realization is leading many scientists to suspect that the concept of finding a single silver bullet biosignature might be overly optimistic. The universe is far too complex and diverse for us to assume that any one molecule, no matter how strongly associated with life on Earth, can serve as definitive proof of biology elsewhere. Instead of searching for individual biosignature gases, the scientific community is increasingly moving toward the idea of building comprehensive cases for life on distant worlds. This might involve looking for multiple different biosignatures simultaneously, searching for seasonal atmospheric variations that could hint at underlying biological rhythms, or trying to detect technosignatures like evidence of pollution or synthetic chemicals that could only be produced by intelligent civilizations. These approaches are significantly more complex and may be beyond our current technological capabilities, but they would provide much more convincing evidence for extraterrestrial life than any single molecular detection could offer. The detection methods themselves also warrant closer examination. When scientists claim to have found a molecule in an exoplanet's atmosphere, they're not actually seeing that molecule directly. Instead, they're interpreting subtle patterns in starlight that has been filtered through the planet's atmosphere, looking for the specific wavelengths that particular molecules tend to absorb. This process is incredibly indirect and relies heavily on our theoretical understanding of how different molecules interact with light under various atmospheric conditions. Small errors in our models or unexpected atmospheric phenomena could easily lead to false positive detections or cause us to miss genuine signals entirely. The statistical confidence levels that scientists use to evaluate these detections can also be misleading to the general public. When researchers report a 3 sigma detection, they're essentially saying there's a 99.7% chance that the signal they're seeing is real rather than random noise. That sounds incredibly convincing, but it's important to understand that this statistical confidence only applies to the raw signal detection, not to the interpretation of what that signal actually represents. Even if we're completely certain that we're detecting a real signal at a specific wavelength, there could be multiple different explanations for what's causing that absorption. The molecule we think we're seeing might not be present at all. Instead, we could be observing the combined effects of several different molecules, unusual atmospheric dynamics, or even instrumental artifacts that we haven't accounted for properly. Furthermore, The instruments we use to make these detections have their own limitations and quirks that can introduce errors into our measurements. The James Webb Space Telescope, despite being the most advanced instrument of its kind ever constructed, is still operating at the absolute limits of what's physically possible with current technology. When you're trying to detect incredibly faint signals from objects located hundreds of trillions of miles away, even the tiniest imperfections in your instruments or unexpected interference can completely throw off your results. The telescope's mirrors, despite being engineered to near perfection, still have microscopic flaws that can affect how light is collected and focused. The detectors that convert incoming photons into digital signals are susceptible to cosmic radiation, temperature fluctuations, and electronic noise. Even the Earth's own atmosphere, despite the telescope being positioned far beyond it in space, can indirectly influence measurements through gravitational effects and reflected light from our planet. All of these factors combine to create what scientists call systematic errors, subtle biases in the data that can be incredibly difficult to identify and correct for. Unlike random noise, which tends to average out over multiple observations, systematic errors can consistently push results in one direction, potentially creating the appearance of a signal where none actually exists. The process of analysing this data also introduces additional opportunities for error. Scientists must make countless decisions about how to process the raw information coming from the telescope. Which wavelengths of light should they focus on? How should they account for variations in the star's own brightness? What mathematical techniques should they use to separate the planetary signal from the stellar background? Each of these choices can influence the final results, and different research teams might make different decisions based on their experience, intuition, or theoretical preferences. This is precisely why we saw such dramatically different conclusions when the Oxford physicist reanalyzed the K2-18b data using alternative methods. The scientific peer review process is designed to catch these kinds of issues, but even this system has its limitations when dealing with cutting-edge research at the boundaries of our capabilities. Reviewers are typically experts in their field, but they may not have access to the raw data or the specialized software needed to independently verify complex analyses. They're often forced to trust that the authors have made reasonable choices in their data processing and interpretation. Moreover, the pressure to publish groundbreaking discoveries can sometimes lead researchers to be more optimistic in their interpretations than the data actually warrants. The competition for funding, prestige, and career advancement in academia creates powerful incentives to find significant results, even when the evidence might be ambiguous. This doesn't mean that scientists are being deliberately dishonest or manipulating their data. Rather, it reflects the very human tendency to see patterns and meaning in ambiguous information, especially when we desperately want to find something significant. When you've spent years of your career searching for signs of alien life, it's natural to be more inclined to interpret borderline results as positive detections rather than inconclusive noise. The history of astrobiology is filled with examples of this phenomenon. In 1996, NASA scientists announced they had found evidence of ancient microbial life in a meteorite from Mars. The announcement made headlines around the world and was even mentioned by President Clinton in a nationally televised address. However, subsequent analysis by other research teams revealed that all of the supposed biosignatures could be explained by non-biological processes, and the scientific consensus eventually shifted away from the life hypothesis. Similar false alarms have occurred with mysterious radio signals from space that initially seemed artificial, but turned out to be natural phenomena, unusual chemical compositions in meteorites that were later attributed to contamination, and atmospheric anomalies on various planets that were eventually explained by previously unknown geological processes. Each of these episodes followed a remarkably similar pattern: initial excitement and media attention, followed by more careful analysis, that revealed alternative explanations, and finally a gradual recognition that the extraordinary claims were not supported by extraordinary evidence. This pattern doesn't necessarily mean that the K2-18b results will follow the same trajectory, but it does suggest that we should approach these claims with appropriate caution and skepticism. The scientific method is specifically designed to be conservative when evaluating extraordinary claims, requiring multiple independent confirmations before accepting revolutionary conclusions. The challenge with K2-18b is that obtaining those independent confirmations may be extremely difficult or even impossible with current technology. The planet only transits in front of its star about once every 33 days, providing relatively few opportunities for observation. Each transit lasts only a few hours, during which the James Webb Telescope must compete with other research priorities and scheduling constraints. Even when observations are possible, the signal is so faint and the analysis so complex that different research teams might reasonably reach different conclusions, even when examining identical data. This creates a frustrating situation where we might never achieve the kind of scientific consensus that would normally be required to confirm such a momentous discovery. Adding to these challenges is the fact that we have no way to directly verify our interpretations through alternative methods. We cannot send a probe to K2-18b to sample its atmosphere directly. We cannot use other types of telescopes to cross-check our results. We are entirely dependent on this one extremely difficult technique of transit spectroscopy, with all of its inherent limitations and uncertainties. The broader context of our search for extraterrestrial life also shapes how we interpret these results. Humanity has been actively searching for signs of alien life for decades, using increasingly sophisticated methods and instruments. The fact that we haven't found definitive evidence yet, despite our best efforts, could suggest that life in the universe is indeed extremely rare. This possibility, sometimes called the Great Silence, has profound implications for how we should evaluate potential biosignature detections. If life is truly rare in the universe, then we would expect most apparent biosignatures to turn out to be false positives caused by unknown, non-biological processes. The extraordinary rarity of life would make extraordinary evidence even more necessary to support claims of its discovery. On the other hand, if life is actually common in the universe, but simply difficult to detect with our current methods, then we might expect to start finding genuine biosignatures as our instruments and techniques improve. Under this scenario, marginal detections like the DMS signal from K2-18b could represent the beginning of a new era of discovery rather than another false alarm. The problem is that we have no way to know which of these scenarios is correct without actually finding life elsewhere. We're caught in a kind of cosmic catch-22 where we need to discover alien life to understand how common it is, but we need to understand how common it is to properly evaluate potential discoveries. The implications of getting this wrong extend far beyond academic science. The discovery of alien life, even microbial life, on a distant exoplanet would represent one of the most significant events in human history. It would fundamentally change our understanding of our place in the universe and could have profound effects on philosophy, religion, and society as a whole. Given these enormous stakes, the scientific community has a responsibility to be extremely careful about how they communicate potential discoveries to the public. Premature announcements or overstated claims could lead to widespread confusion and disappointment when the results are later called into question. At the same time, the public has a legitimate interest in understanding what scientists are discovering and how close we might be to answering some of the most fundamental questions about our existence. The challenge is finding the right balance between transparency and caution, sharing exciting developments, while being honest about the uncertainties and limitations involved. The media also plays a crucial role in this process. Headlines about alien life discoveries generate enormous public interest and engagement, creating powerful incentives for journalists to emphasize the most sensational aspects of scientific studies while downplaying the caveats and uncertainties. This dynamic can create a feedback loop where scientists feel pressure to make their results sound more definitive than they actually are in order to secure media coverage and public attention. The resulting coverage then creates public expectations that may not be realistic given the current state of the evidence. Breaking this cycle requires better communication between scientists, journalists, and the public about how the scientific process actually works, especially in fields like astrobiology, where we're operating at the very limits of our capabilities. The public needs to understand that science often progresses through tentative steps and false starts rather than dramatic breakthroughs, and that uncertainty and debate are normal parts of the discovery process rather than signs of failure or incompetence. The K2-18b study, regardless of whether its conclusions ultimately prove correct, represents an important milestone in our ongoing search for life beyond Earth. It demonstrates that we now have the technological capability to detect and analyze the atmospheric compositions of planets orbiting other stars, something that would have seemed like pure science fiction just a few decades ago. The techniques and methods developed for this research will undoubtedly be refined and improved over time, leading to more sensitive and reliable detections in the future. Each observation, whether it confirms or refutes the presence of biosignatures, adds to our growing understanding of how planetary atmospheres work and what kinds of processes can produce the molecules we observe. The James Webb Telescope is just the beginning of a new generation of instruments that will revolutionize our ability to study exoplanets. Future telescopes currently in development will be even more sensitive and capable of detecting fainter signals with greater precision. Ground-based observatories are also being upgraded with advanced adaptive optics systems that can compensate for atmospheric distortion and provide unprecedented clarity in their observations. These technological advances will eventually allow us to study hundreds or even thousands of exoplanet atmospheres with the same level of detail that we currently achieve for only a handful of worlds. As our sample size grows, we'll be able to better understand the full range of atmospheric compositions and processes that exist throughout the galaxy. We'll also develop better theoretical models for how different types of planets and atmospheres should behave under various conditions. This improved understanding will help us distinguish between genuine biosignatures and false positives caused by unknown geological or chemical processes. The search for life beyond Earth is ultimately a long-term endeavour that will likely span generations of scientists and decades of observations. Individual studies like the K2-18b detection, while exciting and important, represent single pieces of a much larger puzzle that we're still working to assemble. The reality is that, even with all these technological advances on the horizon, we may still be years or even decades away from definitively answering whether K2-18b harbours life. The challenges we face are not just technological, but fundamental to the nature of studying objects that are so incredibly distant and alien to our experience. Think about it this way. Every assumption we make about how atmospheres work, how molecules behave under different conditions, and how life might manifest itself on other worlds is based on our limited experience here on Earth and within our own solar system. We're essentially trying to understand an entirely different world using tools and theories developed for our local cosmic neighbourhood. It's a bit like trying to understand a foreign culture by reading a single book written by someone who has never actually visited that culture. You might learn some things, and you might even get some details right, but there's a very good chance you'll miss crucial nuances or misinterpret important information simply because you lack the broader context needed to make sense of what you're observing. This is precisely the situation we find ourselves in with K2-18b. We're looking at spectral data from a world that is fundamentally different from anything we've ever encountered, trying to interpret that data using models and theories that may not even apply to such an exotic environment. The planet orbits a red dwarf star, which produces a completely different spectrum of light than our Sun. This means that any molecules in the atmosphere will be interacting with radiation that has different properties than what we're used to studying. The chemical reactions, the energy levels, the way different compounds break down or form, all of these processes could work differently under the influence of red dwarf radiation. Moreover, the planet itself is so much larger and more massive than Earth that its atmospheric dynamics are likely to be completely unlike anything we've experienced. The pressure gradients, the circulation patterns, the way different atmospheric layers interact with each other, these could all follow rules that we haven't even discovered yet. When we try to model such an alien environment using our Earth-based understanding of chemistry and physics, we're making a huge leap of faith that the same fundamental processes apply everywhere in the universe. While this assumption is probably correct for basic physical laws, it becomes much more questionable when we're dealing with complex systems like planetary atmospheres. The DMS molecule itself presents another layer of complexity. Even if we accept that it's present in K2-18b's atmosphere, we still need to understand how it got there. On Earth, the production of DMS is tied to very specific biological processes involving marine organisms that have evolved over billions of years in our particular environmental conditions. But what if life on K2-18b works completely differently? What if the organisms there use entirely different biochemical pathways that we haven't even imagined? What if they produce DMS as a waste product rather than as part of their normal metabolism? What if the molecule serves a completely different function in their biology than it does for Earth organisms? These questions highlight just how much we don't know about the possibilities for life beyond our planet. We tend to search for biosignatures based on what we know about life on Earth, but this approach inherently limits us to finding life that is at least somewhat similar to our own. There could be forms of life out there that are so radically different from anything on Earth that they wouldn't produce any of the molecules we consider to be biosignatures. They might use completely different chemical processes, operate at different temperatures and pressures, or even be based on entirely different elements than carbon. This possibility doesn't mean we should abandon our search for familiar biosignatures like DMS, but it does suggest that we need to be very careful about drawing conclusions from negative results. Just because we don't find Earth-like biosignatures doesn't mean a planet is lifeless, and just because we do find them doesn't necessarily mean we've discovered alien life. The statistical analysis that underlies these detections also deserves more scrutiny. When scientists report confidence levels like 3 sigma, they're describing the probability that the signal they're seeing is real rather than random noise. But this calculation assumes that their models and assumptions are correct. If their atmospheric models are wrong, if their understanding of the planet's basic properties is flawed, or if there are systematic errors in their instruments that they haven't accounted for, then those confidence levels become meaningless. The statistics only tell us how likely it is that we're seeing a real signal, not how likely it is that we're interpreting that signal correctly. This distinction is crucial, but often gets lost in the excitement surrounding potential discoveries. A high-confidence detection of a spectral line doesn't automatically translate to a high-confidence identification of a specific molecule, let alone a high-confidence conclusion about the presence of life. The peer review process, while essential for maintaining scientific standards, also has limitations when dealing with such specialized and complex research. The number of scientists who truly understand the intricacies of exoplanets' atmospheric analysis is relatively small, and they often know each other and have worked together on similar projects. This can create a situation where the same assumptions and approaches get reinforced within the community, making it difficult for genuinely alternative perspectives to gain traction. When everyone is using similar models and methods, they may all make similar mistakes or overlook the same important factors. The reanalysis by the Oxford physicist that found no evidence for DMS is a perfect example of why independent verification using different approaches is so important. It shows that the results are highly sensitive to the specific methods and assumptions used in the analysis, which should give us pause about accepting any single study's conclusions as definitive. But even this reanalysis doesn't definitively resolve the question. The Oxford researcher used different assumptions about the planet's atmospheric properties, which may or may not be more accurate than those used in the original study. Without independent knowledge of what K2-18b's atmosphere is actually like, we have no way to determine which approach is more likely to be correct. This uncertainty extends to virtually every aspect of our understanding of the planet. We don't know its exact composition, its atmospheric structure, its surface conditions, or even whether it has a solid surface at all. We're essentially trying to solve a complex puzzle while missing most of the pieces. The James Webb Telescope, for all its remarkable capabilities, is still limited in what it can tell us about distant exoplanets. It can detect the presence of certain molecules in their atmospheres, but it cannot provide detailed information about atmospheric dynamics, surface conditions, or the complex interactions between different atmospheric layers. Future telescopes may be more capable, but they will still face fundamental physical limitations. The amount of light we can collect from such distant objects is inherently limited, and there are quantum mechanical limits to how precisely we can measure that light. No matter how advanced our technology becomes, we will always be working with incomplete and uncertain information when studying exoplanets. This doesn't mean we should give up on the search for extraterrestrial life, but it does mean we need to be realistic about what we can and cannot conclude from the evidence available to us. Extraordinary claims really do require extraordinary evidence, and marginal detections of potential biosignatures probably don't meet that standard. The history of science is filled with examples of discoveries that seemed revolutionary at the time, but were later shown to be incorrect or misinterpreted. The supposed canals on Mars, the cold fusion claims, the faster-than-light neutrinos, all of these were initially reported by reputable scientists using the best methods available at the time. What these episodes teach us is that even the most careful and well-intentioned researchers can be wrong, especially when they're working at the very edges of what's technically possible. The more extraordinary the claim, the more skeptical we should be until the evidence becomes overwhelming. The DMS detection on K2-18b, while intriguing, falls far short of being overwhelming evidence for alien life. It's a marginal signal that depends heavily on uncertain assumptions about the planet's atmospheric properties. It could easily be explained by unknown non-biological processes, instrumental artifacts, or errors in data analysis. Even if the detection is completely accurate and DMS is definitely present in the planet's atmosphere, we still cannot be certain that it was produced by living organisms. The discovery of DMS in comets and other lifeless environments shows that non-biological production pathways exist, even if we don't fully understand them yet. The broader context of our search for life also suggests caution. Despite decades of increasingly sophisticated searches, we have yet to find definitive evidence of life anywhere beyond Earth. This could mean that life is extremely rare in the universe, which would make any individual biosignature detection more likely to be a false positive. Alternatively, it could mean that life is common but difficult to detect with our current methods and instruments. Under this scenario, we might expect to start finding genuine biosignatures as our capabilities improve, but we would still need to be very careful to distinguish between real discoveries and false alarms. The challenge is that we have no way to know which of these possibilities is correct without actually finding life elsewhere. We're operating in a state of fundamental uncertainty about one of the most basic questions in science. Are we alone in the universe? This uncertainty makes it very difficult to properly evaluate potential biosignature detections. If life is common, then marginal detections might be worth taking seriously. If life is rare, then we should be extremely skeptical of anything short of overwhelming evidence, the stakes involved also complicate the situation. The discovery of alien life would be one of the most significant events in human history, with profound implications for our understanding of our place in the universe. The pressure to be the first to make such a discovery creates powerful incentives for researchers to interpret ambiguous results optimistically. At the same time, the scientific community has a responsibility to maintain rigorous standards and not make premature claims that could mislead the public or damage the credibility of the field. This creates a tension between the desire to share exciting results and the need to be appropriately cautious. The media coverage of the K2-18b study illustrates this tension perfectly. Headlines around the world proclaimed that scientists had potentially discovered alien life, while the actual scientific paper was much more cautious and hedged its conclusions with numerous caveats and uncertainties. This disconnect between scientific reality and media coverage is unfortunately common in fields like astrobiology, where the public interest in potential discoveries far exceeds the strength of the evidence available. The result is often a cycle of hype and disappointment that can undermine public trust in science. Breaking this cycle requires better communication between scientists, journalists, and the public about how the scientific process actually works. The public needs to understand that science progresses through tentative steps and false starts, not dramatic breakthroughs, and that uncertainty and debate are normal parts of the discovery process. Scientists also need to be more careful about how they communicate their results, avoiding sensational language and being clear about the limitations and uncertainties in their work. This doesn't mean they should hide exciting discoveries, but they should present them in proper context. The K2-18b study, regardless of whether its conclusions prove correct, represents an important step forward in our ability to study exoplanet atmospheres. The techniques and methods developed for this research will be refined and improved over time, leading to more reliable detections in the future. Future telescopes will be even more sensitive and capable of studying larger numbers of exoplanets with greater precision. This will allow us to build up a statistical understanding of atmospheric compositions and processes across many different worlds, helping us distinguish between genuine biosignatures and false positives. We'll also develop better theoretical models for how different types of planets and atmospheres should behave under various conditions. This improved understanding will help us interpret spectroscopic observations more accurately and avoid some of the pitfalls that may have affected the K2-18b analysis. The search for life beyond Earth is ultimately a long-term endeavour that will likely span many years and involve observations of hundreds or thousands of different worlds. Individual studies like the K2-18b detection are important pieces of this larger puzzle, but they should not be viewed as definitive answers to the question of whether we are alone. In the case of K2-18b specifically, the most honest assessment of the current evidence is that it's intriguing but far from conclusive. The DMS detection could be real, but it could also be an artifact of uncertain atmospheric models or unknown systematic errors. Even if it's real, it could be produced by non-biological processes that we don't yet understand. The planet remains an interesting target for future observations, and continued study may eventually provide more definitive answers about its atmospheric composition and the possibility of life. But for now, we should resist the temptation to draw sweeping conclusions from limited and uncertain data. The question of whether we have found aliens on K2-18b cannot be answered with a simple yes or no. The evidence is ambiguous, the methods are uncertain, and the stakes are too high for premature conclusions. What we can say is that we have detected a potentially interesting signal that deserves further investigation, but falls well short of the extraordinary evidence needed to support extraordinary claims about alien life. The universe is vast and full of wonders that we are only beginning to understand. Somewhere out there, life may indeed exist on distant worlds, producing molecules and exhibiting behaviors that we can detect with our increasingly sophisticated instruments. But distinguishing genuine discoveries from false alarms will require patience, rigorous analysis, and healthy skepticism. Until we have that overwhelming evidence, the question of whether we are alone in the universe remains tantalizingly unanswered. The search continues, and each new observation brings us closer to the truth, whatever that truth may be. But for now, despite the excitement and media attention surrounding K2-18b, we must conclude that the detection of alien life remains an elusive goal rather than an accomplished fact. The scientific method demands nothing less than this level of caution when evaluating claims that could reshape our understanding of life itself. While we continue to hope for that definitive discovery that will finally answer one of humanity's most profound questions, we must remain committed to following the evidence wherever it leads, even if that means acknowledging the limits of what we currently know. The journey toward answering whether we have truly found aliens extends far beyond the confines of a single study or detection. As we stand at this crossroads of scientific discovery, we must acknowledge that the path forward requires not just better instruments or more sophisticated analysis techniques, but a fundamental shift in how we approach the search for extraterrestrial life itself. Consider for a moment the broader implications of what finding life on K2-18b would actually mean for our species. If confirmed, this discovery would instantly transform humanity from a potentially unique phenomenon in the cosmos to just one example among countless others. The philosophical and psychological impact of such a revelation cannot be overstated. Every religion, every philosophical framework, every assumption about our special place in the universe would need to be reconsidered and potentially rewritten. But perhaps more importantly, it would also validate the scientific methods and technologies that made the discovery possible in the first place. The James Webb Space Telescope represents the culmination of decades of international cooperation, billions of dollars in investment, and the collective efforts of thousands of engineers, scientists, and technicians. A confirmed detection of alien life would justify every penny spent and every hour invested in pushing the boundaries of what human technology can achieve. Yet this same pressure for validation creates its own set of problems. When so much is riding on a single result, when careers and reputations and entire research programs depend on finding something significant, the temptation to interpret ambiguous data optimistically becomes almost irresistible. This is not a matter of deliberate deception or scientific misconduct, but rather a reflection of the very human tendency to see what we desperately want to see. The history of science is littered with examples of brilliant researchers who convinced themselves they had made groundbreaking discoveries, only to have their conclusions later overturned by more careful analysis or better data. The phenomenon is so common that psychologists have given it a name: confirmation bias. We naturally tend to focus on evidence that supports our pre-existing beliefs, while downplaying or ignoring information that contradicts them. In the case of astrobiology, this bias is particularly dangerous because the field has been searching for its first major success for decades. Every researcher in the field desperately wants to be the one who finally proves that life exists beyond Earth. This creates a systematic pressure toward optimistic interpretations of marginal results, even when the evidence might not fully support such conclusions. The peer review process is designed to catch these kinds of errors, but it too has limitations when dealing with highly specialized research at the cutting edge of what is technically possible. The number of scientists qualified to properly evaluate exoplanet atmospheric studies is relatively small, and they often share similar training, assumptions, and methodological preferences. This can create echo chambers, where the same mistakes get repeated and reinforced rather than corrected. Moreover, the journals that publish this research face their own pressures. Studies claiming potential evidence for alien life generate enormous media attention and citation counts, which directly benefit the journal's reputation and impact factors. This creates subtle but real incentives for editors and reviewers to be more lenient with papers that make exciting claims, even when the evidence might be somewhat thin. The role of funding agencies also cannot be ignored in this dynamic. Research grants are awarded based on the potential significance and impact of proposed studies. A proposal to search for biosignatures on exoplanets is much more likely to receive funding than one that focuses on mundane atmospheric chemistry with no astrobiological implications. This creates a systematic bias toward research that is more likely to produce dramatic claims, regardless of whether those claims are ultimately supported by the data. These institutional pressures do not necessarily lead to fraud or deliberate misrepresentation, but they do create an environment where marginal results are more likely to be interpreted optimistically and presented with greater confidence than might be scientifically justified. The K2-18b study exists within this context, and we must consider how these broader forces might have influenced both the research itself and its presentation to the scientific community and the public. The challenge of distinguishing genuine biosignatures from false positives becomes even more complex when we consider the sheer diversity of planetary environments that exist throughout the galaxy. Our models for how atmospheres work and how different molecules behave under various conditions are based primarily on our experience with planets in our own solar system, plus theoretical calculations that may not account for all the variables present in more exotic environments. K2-18b represents just such an exotic environment. Its position around a red dwarf star means it receives a completely different spectrum of radiation than Earth does from our Sun. Red dwarfs produce much more infrared radiation and much less visible light than Sun-like stars, which could fundamentally alter the chemistry and dynamics of any atmosphere surrounding planets in their habitable zones. The planet's much larger size and mass also create atmospheric conditions that have no analogue in our solar system. The increased gravity would compress the atmosphere differently, potentially creating pressure and temperature gradients that follow patterns we have never observed. The atmospheric dynamics, the way different layers mix and interact, the chemical reactions that occur at different altitudes, all of these processes could work in ways that our models simply do not account for. When we attempt to interpret spectroscopic data from such an alien environment using models developed for more familiar conditions, we are essentially extrapolating far beyond the range of our actual knowledge and experience. This extrapolation might be accurate, but it could also lead us dramatically astray if the real conditions on K2-18b differ significantly from our assumptions. The detection of DMS itself raises additional questions that go beyond the simple question of whether the molecule is actually present. Even if we accept that DMS exists in K2-18b's atmosphere, we still need to understand the processes that created it and continue to maintain its presence. On Earth, DMS is produced by specific types of marine organisms under particular environmental conditions, but the oceans on K2-18b, if they exist at all, would be radically different from Earth's oceans. The water chemistry, the temperature, the pressure, the types of dissolved minerals and gases, all of these factors could be completely unlike anything we have experience with. If life exists on K2-18b, it would have evolved under these alien conditions over billions of years, potentially developing biochemical pathways that are completely different from anything found on Earth. The organisms might use different metabolic processes, operate at different temperatures and pressures, or even be based on different fundamental chemistry than terrestrial life. This raises the intriguing possibility that DMS on K2-18b might not be a biosignature at all, but rather the product of some unknown geological or atmospheric process that we have never encountered. The molecule could be created through chemical reactions involving the planet's unique atmospheric composition, its interaction with radiation from the red dwarf star, or processes occurring deep within the planet's interior. The discovery of DMS in comets within our own solar system demonstrates that non-biological pathways for producing this molecule definitely exist, even if we do not yet fully understand them. If such processes can occur in the cold, low-pressure environment of a comet's tail, it seems reasonable to assume that other unknown pathways might exist under the very different conditions present on exoplanets. This uncertainty about production mechanisms highlights one of the fundamental challenges in astrobiology: the difficulty of proving that any particular molecule or observation is definitively biological in origin. Without the ability to directly sample the environment or conduct controlled experiments, we are forced to rely on indirect evidence and theoretical arguments that may not be as solid as they initially appear. The statistical analysis underlying the DMS detection also deserves more critical examination. The 3 sigma confidence level that has been reported sounds impressively definitive, but this statistic only describes the likelihood that the observed signal is real rather than random noise. It does not account for the possibility that the signal might be real, but caused by something other than DMS. Spectroscopic analysis involves comparing observed spectra to theoretical models that predict how different molecules should absorb light under various conditions. But these models are based on laboratory measurements conducted under Earth-like conditions, and they may not accurately represent how the same molecules behave in the very different environment of an exoplanet atmosphere. Temperature, pressure, the presence of other molecules, the intensity and spectrum of the incident radiation. All of these factors can influence how a molecule absorbs light, potentially shifting or distorting the expected spectral signature. If these effects are not properly accounted for in the theoretical models, the analysis could incorrectly identify the source of an observed absorption feature. Furthermore, multiple different molecules can sometimes produce absorption features at similar wavelengths, making it difficult to definitively identify which specific compound is responsible for a particular signal. The complexity of exoplanet atmospheres, with their potentially exotic compositions and conditions, makes this problem even more challenging. The instruments used to make these observations also introduce their own uncertainties and potential sources of error. The James Webb Space Telescope, despite being the most advanced instrument of its kind ever built, still has limitations in terms of sensitivity, spectral resolution, and systematic errors that can affect the accuracy of its measurements. Cosmic radiation can interfere with the detectors, creating false signals or corrupting real ones. Temperature fluctuations can cause the instruments to behave slightly differently over time, introducing systematic biases that are difficult to correct for. Even tiny imperfections in the telescope's mirrors or other optical components can affect how light is collected and analysed. These instrumental effects become particularly problematic when dealing with very faint signals, as is the case with exoplanet atmospheric studies. The signal from the planet's atmosphere represents only a tiny fraction of the total light coming from the star system, requiring extremely precise measurements to detect and characterize properly. When you are operating at the very limits of instrumental sensitivity, small systematic errors that might be negligible under normal circumstances can completely dominate the results. This makes it extremely difficult to distinguish between genuine detections and instrumental artifacts, especially when the expected signal is already very weak. The data processing and analysis methods used to extract planetary signals from telescope observations also introduce additional opportunities for error. Scientists must make numerous decisions about how to handle the raw data, which wavelengths to focus on, how to account for stellar variability, and what mathematical techniques to use for signal extraction. Each of these choices can influence the final results, and different research teams might reasonably make different decisions based on their experience and theoretical preferences. This subjectivity in the analysis process means that the same raw data can potentially yield different conclusions depending on who analyzes it and what methods they choose to employ. The reanalysis of the K2-18b data by the Oxford physicist provides a perfect example of this phenomenon. Using different assumptions and methods, he reached completely opposite conclusions about the presence of DMS in the planet's atmosphere. Neither analysis is necessarily wrong, but they demonstrate how sensitive these results can be to the specific approaches used. This sensitivity to methodology raises serious questions about how confident we can be in any particular result, especially when the stakes are as high as they are for potential biosignature detections. If two equally qualified scientists can examine the same data and reach opposite conclusions, how can we know which interpretation is correct? The answer, unfortunately, is that we often cannot know with certainty, at least not with our current capabilities and understanding. This fundamental uncertainty is uncomfortable for both scientists and the public, who naturally want clear, definitive answers to important questions. But it is also an inherent part of doing science at the very frontiers of what is technically possible. The challenge becomes even more complex when we consider the broader context of our search for extraterrestrial life. The detection of DMS on K2-18b, even if completely accurate, represents just one piece of evidence from one planet among the billions that exist in our galaxy. Drawing broad conclusions about the prevalence of life in the universe based on a single, marginal detection would be scientifically inappropriate. If life is truly common in the universe, we should expect to find biosignatures on many different worlds as our observational capabilities improve. The fact that K2-18b might harbour life would be exciting, but it would not be particularly surprising under this scenario. We would simply be witnessing the first of many such discoveries. On the other hand, if life is extremely rare in the universe, then any individual biosignature detection becomes much more likely to be a false positive. The extraordinary rarity of genuine biological signals would mean that the vast majority of apparent detections would turn out to be caused by non-biological processes or instrumental artifacts. The problem is that we have no way to know which of these scenarios is correct without accumulating much more data from many more planets. We are essentially trying to solve a statistical problem with a sample size of 1, which is fundamentally impossible from a scientific standpoint. This uncertainty about the broader context makes it very difficult to properly evaluate the significance of any individual result. Should we be excited about the K2-18b detection because it might represent our first glimpse of alien life? Or should we be skeptical because the history of astrobiology is filled with false alarms and premature claims? The honest answer is that both reactions are probably appropriate. The detection is exciting enough to warrant continued investigation and follow-up observations, but it is also uncertain enough that we should avoid drawing definitive conclusions until we have much stronger evidence. This balanced approach requires a level of patience and intellectual humility that can be difficult to maintain in the face of such a potentially momentous discovery. The natural human tendency is to want immediate answers to profound questions, but science often requires us to accept uncertainty and wait for better data before reaching conclusions. The media coverage of the K2-18b study illustrates the challenges of communicating this kind of nuanced scientific uncertainty to the general public. Headlines proclaiming the potential discovery of alien life generate enormous interest and engagement, but they can also create unrealistic expectations about the strength and certainty of the underlying evidence. The result is often a cycle of hype and disappointment that can undermine public trust in science and make it more difficult for researchers to secure support for future studies. When preliminary results are presented as definitive discoveries, the inevitable corrections and qualifications that follow can make it appear as though scientists do not know what they're talking about or are deliberately misleading the public. Breaking this cycle requires better communication between scientists, journalists, and the public about how the scientific process actually works. The public needs to understand that science progresses through tentative steps and false starts, not dramatic breakthroughs, and that uncertainty and debate are normal and healthy parts of the discovery process. Scientists also have a responsibility to be more careful about how they present their results, avoiding sensational language and being clear about the limitations and uncertainties in their work. This does not mean they should hide exciting discoveries or downplay their potential significance, but they should present them in proper scientific context. The peer review process, while essential for maintaining scientific standards, also needs to adapt to the unique challenges posed by astrobiology research. The traditional model of peer review assumes that expert reviewers have access to similar data and can independently verify the results of a study. But in the case of exoplanet research, the raw data is often extremely complex and requires specialized software and expertise to analyze properly. This creates a situation where reviewers may be forced to trust the author's data processing and analysis methods without being able to independently verify them. While this is not necessarily problematic, it does place additional responsibility on the authors to be transparent about their methods and honest about their uncertainties. The development of open data policies and standardized analysis tools could help address some of these issues by making it easier for independent researchers to reanalyze and verify published results. This would provide an additional layer of quality control beyond the traditional peer review process and help identify potential errors or biases in the analysis. Looking toward the future, the search for life beyond Earth will likely require a more systematic and statistical approach than the current focus on individual planets and detections. Rather than trying to definitively prove that any single world harbors life, we may need to build up a statistical case based on observations of hundreds or thousands of different planets. This approach would allow us to identify patterns and trends that might not be apparent from individual studies, while also providing the large sample sizes needed to properly evaluate the significance of any particular result. It would also help us develop a better understanding of the full range of atmospheric compositions and processes that exist throughout the galaxy. Future telescopes currently in development will make this kind of systematic survey possible by providing the sensitivity and efficiency needed to study large numbers of exoplanets in detail. Ground-based observatories are also being equipped with advanced adaptive optics systems that can provide unprecedented clarity in their observations of nearby star systems. These technological advances will eventually allow us to move beyond the current era of individual, marginal detections toward a more comprehensive understanding of planetary atmospheres and the potential for life throughout the galaxy. But this progress will take time, and we must be patient as the field develops and matures. In the meantime, studies like the K2-18b detection serve an important role in pushing the boundaries of what is technically possible and developing the methods and techniques that will be needed for future discoveries. Even if the current results turn out to be incorrect, they represent valuable learning experiences that will inform and improve subsequent research. The question of whether we have actually found aliens on K2-18b ultimately cannot be answered definitively based on the current evidence. The detection is intriguing and worthy of follow-up investigation, but it falls well short of the extraordinary evidence needed to support such an extraordinary claim. What we can say with confidence is that we are living through a remarkable period in the history of science, when for the first time we have the technological capability to search for signs of life on worlds orbiting other stars. The techniques and instruments we are developing will only become more powerful and precise over time, bringing us ever closer to answering one of humanity's most profound questions. Whether that answer comes from K2-18b or from some other world that we have yet to discover remains to be seen. But the search itself represents one of the greatest adventures in human history, pushing us to develop new technologies, expand our understanding of the universe, and confront fundamental questions about our place in the cosmic order. The universe is vast and full of wonders that we are only beginning to explore. Somewhere among the billions of planets that orbit the countless stars in our galaxy, life may indeed exist in forms that we can barely imagine. Our continuing efforts to find and study these distant worlds bring us ever closer to that ultimate discovery, even as they remind us of how much we still have to learn about the cosmos and our place within it.